Elon Musk is putting $25 billion on the table to build the largest artificial intelligence chip factory in history. The goal is 1 terawatt of annual computing power. The manufacturing will happen in Austin, Texas, but the vast majority of these chips are destined for low Earth orbit. Musk is attempting to bypass the established global foundries entirely. He is making a direct bid to own the semiconductor supply chain for every company in his portfolio. This timeline chart shows Samsung's original delivery date for its 2-nanometer manufacturing process in Texas, and how it slipped backward by 6 months. 2 nanometer refers to the extremely dense, advanced generation of semiconductor manufacturing. That delay pushed Tesla's AI6 tape-out directly into the red. A tape-out is the final step where a chip's design is completed and sent to the factory to be physically manufactured. Without those processors, Tesla's immediate product roadmap stalls. The Cybercab robotaxi launch had to rely on older hardware, and the mass deployment of Optimus humanoid robots faces direct hardware constraints. Relying on external suppliers is capping the speed at which Tesla can operate. Controlling the physical compute hardware is now an absolute requirement to keep these programs moving. The proposed solution is a massive facility right on the Giga Texas campus. This building is designed to handle every single step of chip production: design, lithography, fabrication, memory integration, advanced packaging, and comprehensive testing. This flowchart illustrates the traditional global chip supply chain collapsing into a single localized building. The production targets are aggressive, starting at 100,000 wafer starts per month and scaling to 1 million. Wafer starts is the industry metric for how many silicon disks a factory can process. 1 million wafers equals roughly 70% of TSMC's entire global output. By putting the designers and the fabrication machines in the same building, engineers can test a chip, analyze the results, revise the mask, and manufacture a new version without ever shipping parts across the ocean. This donut chart shows exactly where that compute is going, with a clear 80-20 split. Only 20% of the output is for Earth-bound vehicles and robots. The other 80% consists of D3 chips. The D3 is a high-power, radiation-hardened processor built specifically to survive the harsh environment of space, destined for a planned 1 million satellite constellation. Moving data centers into orbit solves the 2 main bottlenecks of AI scaling on Earth: electricity and heat. Satellites capture 5 times more solar irradiance, the amount of power received from the sun per unit area, and the vacuum of space provides natural heat rejection. Terafab is designed to be the manufacturing engine for a network of off-world AI data centers. This bar chart contrasts Terafab's $25 billion budget against historical reality. TSMC spent $165 billion to build Arizona fabs, not reaching 2-nanometer production until 2029. Furthermore, actual fabrication requires strictly limited $400 million ASML scanners and years of specialized engineering. The semiconductor industry measures progress in years, not months. The strategy here assumes that the rapid iteration cycles that work for software can be applied to the precise physics of subatomic manufacturing. If this works, Musk captures the entire AI hardware stack. If it fails, he sinks $25 billion into an empty factory, while his core automotive business is already facing a decline in global sales. The 1 terawatt goal is a distraction from the immediate hurdle. The true test is whether the prototype facility, currently under construction in Austin, can produce a single functional batch of silicon. Until we see a verified 2-nanometer chip come off the line in Texas, Terafab is a $25 billion blueprint waiting to be tested.